Okay, thank you everyone for joining us on this fifth version of our seminar series on compassionate mathematics. I'm very happy to welcome Nathan Haydon to present to us work on Peirce's existential graphs and string diagrams for first-order logic. This is work that he did recently. He defended for his PhD thesis in Tallinn. But I'll invite Nathan to tell us a little bit more about his story, how he came to this topic, and how he sees compassionate math reflected in it.
Great, thanks, Ted. Yeah, I'll start a bit with because the whole talk is kind of an introduction to this topic, but of Peirce's graphs and string diagrams. But I'll start with, as we tend to do in these compassionate math series, to mention a few words about what compassionate math is for, at least from the point of view of this project. And to me, it means, again, at least confined to this project, that develop this, the community one should develop more accessible notations. And I think there's kind of a sense that most people would agree with that this is helpful for at least better instruction, so for teaching or for beginners. But I want to suggest a slightly bolder claim that I think many of us here will also probably agree with, that better notations is better for research. It helps clarify our thoughts. It helps us avoid kind of either mistakes or erroneous superficial parts of notation or derivation, and it ultimately, I think, helps us develop the field. I'll add too that I think another important component of this work, but also just compassionate math in general, is that it's this idea is not kind of dogmatic or static, but that we need to constantly be on guard for finding mathematics in new and surprising places. And this project in particular that I've been doing, where I've been trying to modernize this very old graphical notation, is an example of that. But I also think that Peirce's initial work is an example of that as well. So Peirce kind of took on these projects. He was committed to them. He wrote a lot about them. And this talk is a demonstration of a lot of that. So I'll begin. What's the aim today? Well, I'm going to tell the story of Peirce's early developments in graphical logic, and so it's going to serve as broadly as an accessible introduction to diagrammatic or graphical logic. Slightly more specifically, it's going to be an accessible introduction to Peirce's graphical logic in particular, which he called the existential graphs, and the connection that has to recent developments in categorical logic.
Nathan,
And all these descriptions, I think, this is kind of a telling the story in Peirce's own words, or at least the best as I can. So these descriptions and examples all come from Peirce, which I think is a neat kind of side story of the work.
Sorry to interrupt, Nathan. I just wanted to make sure everyone knows that, and to ask if you are comfortable with being interrupted with questions, and maybe whether people know to raise their hand or put questions in the chat, and we will be monitoring and interrupting it.
Yeah. Please feel free to ask questions.
We want to keep it interactive.
Yeah.
All right.
Yeah.
Go ahead.
So the overall aim is that, or the kind of goal or the result to take away from the talk will be that Peirce's concern for developing a better logical notation both led to his work on the graphs and also led to recent advances in string diagrams and in categorical logic. So what are the graphs? Well, they're a graphical calculus for reasoning about relations developed by Peirce from the 1890s to 1914. He began studying, these are just cool images, so just take a look at them, but don't worry about reading them. Natural language sentences and drawing inferences from them. He explored notions of logical connectives and different modalities, different ways of representing entailment or consequence relations. He drew more complicated graphs. These are his notions of multitudes. I think they look neat. But for the most part, this none of this work caught on. So Peirce had only one published paper in his lifetime on the graphs. It was on a very early version that he ended up abandoning shortly thereafter. And he only gave one public lecture on the graphs. And until at least quite recently, it was hard to find a bulk of Peirce's writings on the graphs. This is changing right now. The book that's on in the upper right corner there is still coming out, but there's a new volume that it's 5 volumes that combines most of Peirce's writings on the graphs. So why should we care about this very old notation? Well, Peirce presented some of the earliest instances of string diagrams as we might recognize them today, and stated some essential features and laws. So here's an example of the associativity of addition. So he suggests that we take S here as a node for sum, taking an input value, U and V, and the output W is the addition here. And if we kind of squint, we can see that this center left graph is the associative operation, right? If we label the lines on Peirce's graph, and we label them as the input values of this shows that given 3 values, X, Y, and Z, there's a W that is the same as if we take X and Y and add them first and then add Z, and if we had taken Z or Y and added them first and then added X afterwards. The graph on the center right here is commutativity. So we can do the same thing. We can label these. We see that if U plus V is W, then V plus U is W. And the graph on the right here is actually Peirce's, it's the existence of negative values or minus quantities. So it has a summation, but it has a kind of neat feedback loop in this. So I'm already kind of way ahead of how to interpret the graphs and see them, but it's a nice example that we might immediately be familiar with if we've seen associativity and commutativity of string diagrams.
I'm sorry to interrupt, Nathan, but I think
Yes.
this might be a great time. If you can bring back the previous slide for just a
Yes.
second. And I want to make sure that people, don't have any questions. Give everyone the benefit of an extra minute to figure out on their own the basically the stringing together of the labels that is going on outside of the box that basically identifies different inputs together to make this work.
Yes.
And the very fact that you can draw it is a instantiation of the law itself, right?
Yeah. So the wires capture kind of the sameness of the value or the variable. And then this Peirce calls it a scroll, these nested loops. And that means an inclusion or an implication. But I'll describe this in a bit more detail.
Okay. All right. Just to...
Yeah. We're going to start way back. Yeah. So what's the outline for the talk? I'm going to talk first about the propositional case, so kind of a simplified version of Peirce's graphs. And then I'll add variables for first order logic. This Peirce called the beta variant of his graphs. And then I'll give a modern presentation that appeals to string diagrams for Cartesian bicategories at the end. So let's look at Peirce's alpha here, which is just going to be propositional logic. Now the blank on the screen here is it's just a blank slide to signal the coming of the next section, but Peirce actually thought it was quite important to put a name to this, because when we scribble something on the page to engage in a diagrammatic or graphical reasoning, we start with a blank page. And Peirce had a special name for this. He calls it, at least in this logical context, he calls it the sheet of assertion. And it represents this is the convention, it represents the universe of discourse. So what we write on it is what we will take to be true, and what we will take to be true to then further reason about. So here's an example. He says the lilacs are in bloom. So what does this mean? Well, it means that in the universe that we're talking about, so in what we're taking to be the case and what we're going to reason about now, are that the lilacs are in bloom. Here's another example. A pear is ripe. Again, these all come from Peirce, but it's kind of neat to repeat them here. So in this world that we're going to reason about, the pear is in fact ripe. Now, one thing that we can do almost immediately, we can assert several things. Okay, so I've started here with it hails, and now I've added an additional expression, it is cold. Now, it almost goes without saying, but it's worth saying that juxtaposition here is conjunction. Now, I say it almost goes without saying because we kind of just by writing them together and kind of reading them, we've already in some ways taken them to be asserted together. But this is an important point that Peirce draws our attention to. So he says that this means kind of a conjunction here, that it hails and it is in fact cold. And the next thing Peirce does is that this leads, I think, quite naturally into his first inference rule for the graphs. So we have these statements that are on the sheet, it hails, it is cold, and we can selectively erase those statements. So we could erase the it is cold, we could, and a nice way of kind of summing this up is that we can, once we've said them, we can unsay them. Peirce says elsewhere that it's kind of like we asserted several things, but now we have decided to focus our attention on just one of them. So the other one is kind of flown off the screen, say. But be that as it may, we could have asserted the other one, or so we could have erased the other one, or we could erase both. And Peirce's justification for this is that if it is the case that it hails and it is cold, then it is in some sense true that, or continues to be true that, it hails. And so again, this is why it serves as a nice inference rule. We have not done anything disingenuous. We've in fact just, in kind of eliminating one term, we've just kept something that we've already asserted. And likewise, we could have said it hails and it is cold, then it is further true that it is cold. And we could have just erased both and ended up back at the sheet, which is the blank. So if we see this as a representation as the sheet itself, we kind of, in some ways, started with it. And so to give, if we wanted to put it in the same form as the previous examples, we started with this background universe of discourse that we take to be the case. And now we're just repeating that same universe of discourse is holding as we persist.
Nathan, can I ask a quick question?
Yes.
Is there the implication that anything that is said can be unsaid, and ought we be worried about that at all? In the back of my mind, I worry perhaps that this might lead to something undesirable.
Let me see if this is getting what if this is part of your worry, is that I would be careful to distinguish when we unsay something. It's not that we deny it or take it no longer to be the case. It's just that it's not the focus of our attention anymore. And so it's kind of gone back into, so that's one reason why I brought up this case where Peirce sometimes described it as it's just gone elsewhere on the sheet. So we're not attentive to it anymore. It's still there. It's still kind of could be agreed to if we were to bring it up again, but it's no longer the focus of our attention. Does that kind of help a bit?
Yes, absolutely. Okay. Thank you. It's different. Okay. Yeah.
Okay, so we have these statements that we just write, these natural language statements that we write on the sheet. We take them to be true. And we imply that juxtaposition of them serves as conjunction on the sheet. And Peirce really just adds one more kind of element to the syntax, one other graphical notion, and that is what he calls the cut. And the cut is a circle that he goes over one of the statements or a number of statements. And this cut serves as negation of that statement. So an example would be, right, before we had it hails and it is cold, now we have it hails and it is not cold. And so one way to think about this cut is that it kind of serves as a separation from, separating that term from what is actually asserted in the universe of discourse. So in this case, it's not cold. And once we have that, because this is classical logic, we can actually assert a number of different things. So we can, by how these are nested. So we could have said, it does not hail and it is not cold. That's the center left here. Now we could interpret the center right as it's not the case that it does not hail and is not cold. But that shares the same meaning as disjunction. And so this one way of reading this graph is that it hails or it is cold. And the graph on the right, again, we could read it kind of as negation and conjunction from outwards inwards, or we can just see it as a sign of implication or inclusion. So if it hails, then it is cold. And one way that I kind of do this visually is that when I read these kind of these nested cuts, I kind of imagine going into the first outermost and then having this disjunctive option to choose one of the two sheets to then go into, to move into. And likewise, when I see this if then, I kind of break it off into this antecedent area, this once enclosed space, this outermost place, and see it as an if, and then this innermost connection as the consequence, as a conclusion of the implication. And when you become fluent in these graphs, you just kind of read these off, and we're actually allowed to kind of change them as we these for example, we could read the disjunction as an implication if we wanted to as well. Now, one thing that follows from just having this notion of nesting is that we have these, one way we should see this is kind of a hierarchy of sheets of assertion. So we have it hails as kind of the outermost sheet. It's not enclosed by anything. And then inside, in the once enclosed spaces, we can assert other things. But they are in some ways within or under or subsumed by the larger sheet of it hails. And likewise, we have these doubly enclosed spaces that are now, Peirce calls them evenly enclosed again. Now I'm going to give an example about why this works, but it's just, I'm kind of just getting at there's this natural hierarchy of sheets that's happening here with this notational choice. So let's look at a very basic example that Peirce gives, right? So this is just going to be modus ponens, probably the most basic example in logic. So if it is the case that it hails, and if it hails and it is cold, we can conclude that it is cold. That's modus ponens. And I'm going to show you how Peirce, the inference rules that Peirce uses to derive this. So the first thing that he does is that he notices that we've asserted it hails, and this is where that hierarchy of the sheets is important. We've asserted on the sheet itself that it hails. And so we're going to, in this more minor context, deiterate it hails because we've already in some sense asserted it. And now here we have a blank saying that in this universe, so if this sheet holds, then it is the case that it is in fact cold. And so Peirce then moves to, because in this universe it is cold, this double cut can be erased. So then he erases both of these. This is called double cut elimination. And then he erases the it hails using that earlier rule, and now we're left with it is cold. And so to put all this together, we've gone from it hails, and if it hails and it is cold, to it continues to be true that it is cold, right? So this is kind of a basic deductive step in inference. We've done it graphically using these three rules that Peirce takes to be primitive, which is this deiteration, this double cut elimination, and this erasure. So what's the overview of this basic kind of propositional system for logic? Well, we have these asserted statements. So these are those full sentences that I was showing that Peirce thinks are quite natural just to write down. We often just use variables to describe them. So that's why I have the P, Q, and R. We have this notion of a cut, this circle. And we have these conventions that the sheet of assertion takes as given, a universe of things that we take to be true. That juxtaposition on the sheet serves as conjunction, and that cut serves as negation. And then we have these three inference rules, the twin inference rules of erasure, insertion, iteration, deiteration. I'm going to describe these. I'm going to go on to describe them now. And then this add removing of the double cut. And I flagged that there's another one kind of lurking in the background of these rules, which is the principle of contraposition. So I think it helps us kind of better account for what some of these inference rules are. So what are these inference rules? Well, the first one, erasure.
Nathan?
Yes.
A quick question. I wonder if you can tell us whether this representation that you're giving, if Peirce if you know whether Peirce originally was kind of coming up with it with the interest of formalizing his inference. In other words, kind of like analogous to Boolean expressions or other forms of formalizing logic, or he was looking to help himself make new inferences. I don't know if my distinction is
No,
sufficient.
good, good. He yeah, so a bit of the history of Peirce's development of the graphs. So he was a logician and mathematician, and he was working on what we would call in kind of using kind of basic linear algebraic syntax. He was working on what we would now recognize as relation algebra. And this goes back to De Morgan and Schroeder and Boole. And Peirce tried to generalize Boole's calculus to the logic of relations, and that was led to a paper that Tarski ended up basing the work on relation algebra on. But this was all back when he had this algebraic syntax, and Peirce was so he was very familiar with the more traditional syntax. And he developed this graphical formalism as a way to better represent the inferences and the inference rules, and to overcome what he thought were some limitations of the syntax that was used at the time by De Morgan and Schroeder and Boole. And so I could chat a bit more about what he thought those limitations were. But he was very fluent, at least at the time, with other work on the algebra of logic tradition and the logic of relations there. And he really saw this as an advancement, as a better notation coming out of his work on that. Yeah. Good. So the first rule here is that erasure rule that I hinted at. This is kind of meant as an implication. This is Peirce's kind of peculiar, and it's not peculiar, it's just idiosyncratic, his symbol for that. Iteration is that if we've, well, I'll give you it in Peirce's words here. Any graph may be iterated within additional cuts, and any graph could be so iterated, it may be de-iterated by erasing the inner replica. Okay, so we can iterate the P inwards into a cut, and if there's a P in the outer region, we can de-iterate it to go back in the other direction. We can add or remove a double cut at will, as long as there's nothing in between them. And this principle of, oh, this is it, but this is straightforward reading. So the double cut may be inserted around or removed from any graph on any area. And the principle of contraposition, which Peirce says is if any transformation is, he says he has a fancy word for this, but is graphically valid under even enclosures, then the reverse transformation is valid under odd enclosures. So if we can transform P into Q, then in a cut context, we can go from Q to P. And this gives us the twin insertion rule at the top here. So in a cut context, so we could have erased the P on the sheet, but in a cut context, we can add a P. And it's what I've tried to do in this like kind of introduction to kind of some of the intuitions that Peirce was working with in the development of this calculus is to show how these correspond to somewhat basic intuitions about asserting, right? So erasure is to unassert or to kind of unsay something that was said. I call this the insertion rule, the type of test assertion where we add a graph inside of a cut context. Iteration, de-iteration is that we have this precedence, this hierarchy of universes that we can move inwards or we can pull outwards if we want. Every assertion follows from the sheet itself is a way of interpreting this double cut rule. And then the principle of contraposition reverses this direction of rewrites. And what's interesting is that that is sufficient for classical propositional logic. So this system is quite different from how propositional logic is traditionally accounted for in textbooks. But these are fairly basic rules that may be unfamiliar to us, but they once you start using them, they're quite simple for what they are. And it's kind of remarkable that I think this alternate set of rules is possible and that it actually does and serves as an account of propositional logic. And you can find a nice description of this in Don Roberts has probably one of the only, but still an introductory textbook on the graphs called The Existential Graphs of C.S. Peirce.
I think Niels has a question.
Yes, Niels.
Yeah, just a quick question. Can you avoid the rule of contraposition if you like assume erasure and on even layers and insertion on odd layers?
Yes.
Or?
Yes.
Okay.
Yes. Okay, so now I'm going to turn to the next version that Peirce calls beta of the graphs. And this is now first order logic with equality. And to do this, I'm going to go over again, kind of in the same way, these step-by-step intuitions that Peirce was working with to develop the calculus that I just showed, this propositional case where you write down a complete statement, to one where you have things like variables and you have somewhat more complicated expressions. So Peirce started with statements, again, like this, like a leaf rustles over the ground. And he noticed that you can break this up into kind of sub-relations or sub-statements that by having these holes in the expression. And Peirce has a fancy word for this. He calls it reams and remata, but I like seeing it as like an incomplete relation. And this blanked, he noticed a nice way to just, again, in natural language express it is we just say, read this blank as something. So a leaf rustles over the ground is a complete statement, but we can have a blank say something rustles over the ground, or a leaf rustles over something, or something rustles over something, or we can have this kind of most general binary relation, which is just something over something. And I've written it this way in part because once we do this, we also notice that there's a bit of a kind of logical ordering to this, right? If we assert that a leaf rustles over the ground, we can kind of weaken that to say that something rustles over something or something is over something. And this order will come back to us when we talk about the inference rules for these lines.
Nathan, this
Yes.
reminds me vaguely of syntactic trees. Is this a valid analogy, or am I being misled?
I think so. So I'm not sure though, because I don't know enough about syntactic trees, but certainly like an expression in the graphs, because you have these nested cuts, you can generate a tree form for this. I'll also give some other examples about later when we have these lines actually end up branching. So then there's actually maybe another kind of at least an intuitive connection to this.
Thank you.
So here's another example, also from Peirce. God gives some good to every person. And so this most generally appeals to a triadic relation. Someone gives something to someone. But we can generate all these other kind of sub-relations based off of this one statement. And Peirce has in mind here, as he continues to develop this notion, he particularly likes these triadic notions. And he starts to form them, draw them as branching. And he has in mind here valency in chemistry, where you kind of combine molecules to form larger compounds. And so he starts to see relations. And this, I think, is a really interesting observation. He was actually a bit of a chemist, so this is probably where this came from. But he started to see relations as having these binding sites where you can now combine and plug in other relations to form larger expressions and statements. Let's see. And so here we can take someone gives something to someone and something rustles over the ground, and we can combine them to form someone gives something that rustles over the ground to someone else. And so we can form these more complicated expressions through composition. And Peirce notices that this branching of a line asserts, just like a regular line, that has continuity. It has continuity of identity. So it's an identity relation. This branch means the same as. And this leads to this expression, if I already didn't say it, that Peirce called these lines of identity. Here's another example. So this is something, someone maybe is Nordica, is a woman, and sings. And again, now we can erase sections of this line in the same way that we took a statement and filled in and broke it down by adding blanks into a sub-expression. We can now erase aspects of this line to draw inferences about more general claims about this statement. So if we erase that line that I showed, now it says something is Nordica and something is a woman who sings. We could erase another line that says Nordica sings and something is a woman, or Nordica is a woman and something sings, or we can erase all these connections and say something is a Nordica, something is a woman, and something sings. Peirce adds just one kind of final component to this, which is that an explicit sign for existential quantification, so for existence. So sometimes saying something sings is kind of like saying there's a variable for sings, but not that's necessarily that something exists. So on the sheet of assertion, he adds this node here. These are both in the center, at least, is in Peirce's own hand, but he goes on to give another this closed loop that kind of comes back in on itself. He sometimes simplifies it just as a node here. And when we combine that now with the cut from before, we can generate expressions with quantification. So we have somebody sings on the left, somebody does not sing with the negation here in the center left. Center right is nobody sings. And then everyone's favorite here, everybody sings on the right. So within a cut context, this line, this existential quantification, because it's negated, becomes a universal quantification.
Nathan, just to be clear, from your previous slide, if you don't mind, the difference you're trying to draw is that just one more. Yeah. So on the very left, when it's just a blank line, it's simply the statement that something sings, somebody sings. Whereas when you put that closed loop, the intent, or when Peirce does, the intent is something exists which sings. Is that right? There's a existential operator there?
Yeah.
Okay.
Yeah, that's right. So in the modern version that I'll get to in the last section, one serves as just a variable for sings, and the other is actually quantified over. So we can treat frame-bound variables. Now, Peirce doesn't have any of those, or doesn't. I mean, that didn't really exist in his time, even though he is generally recognized as one of the first to understand quantification. But I think the way that he describes the one on the left, he doesn't describe it as a free variable, because again, he doesn't have these terms, but he describes it kind of as a relation of sings, but not necessarily that something exists that fulfills that yet.
Sorry, is it okay to think of that as a sort of, I mean, I'm thinking of it as a sort of a dangling connection, like a binding. Using the binding idea, it's a dangling binding. It's not syntactically correct.
Yeah, that's right. So we see this in some ways as it's still open, where the one on the right is now closed because it's actually been quantified. Yes. So if that intuition helps, great. So now with this, we can generate quite complicated expressions. Here's another nice one. This is again in Peirce's hand on the left, or my copy of my duplicate of an expression in Peirce's hand, and a version on the right. So the way to read this, we have some artist, right? So we have an artist, and everything that they look at, they see beauty in. And so this is Peirce writes, an artist sees beauty in all they look at. So the very same thing that they look at and they see beauty in is kind of carried over by this line of identity in the conclusion here. And the nice thing, a kind of, I think, very neat thing about going from this propositional case to one with, yes, then.
Sorry, Nathan. Is there a reason? Can you go back? Yeah. It was just a little too quick. I think I can maybe try to figure it out myself, and I'm sort of, maybe others are in the same place. But I'm wondering what the import is of the two connections.
Okay,
And
of the two separate wires.
the two separate wires, one on the one
Yes.
side and one on the other side.
Yeah. Yeah. Okay. So I'll try to. The confusion might be because I didn't speak clearly enough. So I'm going to try to do it again here. So the wire on the left says there's something that is an artist, which we take to exist because it's on the outermost section, and that artist looks at and sees beauty in things. Okay.
Right. So these two separate things, basically.
These are separate things. So this other wire says these are the things that the artist looks at, or that the artist sees beauty in. But because that wire is connected, those are the very same things.
I see.
So it's kind of, again, the sameness of the object here, the sameness of the variable.
So am I, just to say it in my words, maybe it'll help
me. Yeah.
If that second wire, the wire on the right was not there, the statement would be the artist looks at some things and sees beauty in some things. Whereas putting that extra connection says that whatever the artist looks at is also what they see beauty in.
Yes, that's right. Yes.
Okay.
Okay, so one of the nice things about the move from alpha to beta for Peirce, so by adding these lines of identity, is that nothing changes in the inference rules. There's very slight modifications, which I'll get to. But the syntax and the conventions are the same. Now we just add lines of identity. So we still just have statements, cuts, and now we have these little lines. And we, as a convention, take this line of identity to assert that something exists or something is. And the inference rules largely stay the same. And so this gives kind of the classic picture of Peirce's beta graphs. Again, you can find more information about it in Roberts. But now I'm going to go over those inference rules, but I'm going to connect them to this modern notion of Cartesian bicategories and string diagrams for Cartesian bicategories. And so I'm going to elaborate on the kind of the right side of this story here. So let's look at this modern reconstruction of Peirce's beta graphs. So Cartesian bicategories of relations are a kind of a categorical presentation of relations from 1987. And there's a nice string diagrammatic version of them in a paper by Filippo and Jens and Pavel from 2018. There's another paper by Fong and Spivak on, I think it's graphical regular logic. But these are string diagrams for a well-behaved fragment of first-order logic that just has existential, quantification, and conjunction, and top. And it uses, think of this, these are like elements of the syntax and kind of like building blocks like Lego, as it's often described. You can kind of plug them in to form expressions. And they have, with that, several inequations, these bottom section here for inference rules, and this top expressions for qualities. And Peirce doesn't need to use these. They're very much like Peirce's lines of identity. I think actually I would just prefer to call them lines of identity, really. So we think often about these nodes, this black node as being copy, as asserting sameness or equality. And this is the same thing that Peirce is getting at with lines of identity. So that was kind of the inspiration for moving to this account with string diagrams. And again, Peirce doesn't, because it's just sameness, because these are a branching of an identity relation, he doesn't need to assert associativity and commutativity. Those are these first two lines. Maybe you'd recognize them from the very first example, or this unit. And he also doesn't need to assert these topological equivalencies in the center or the special equation here in the below center. But what's remarkable about Peirce is that he was very much interested in what he called the teridentity or triidentity relation, which is a branch off of the line of identity. And because he was interested in how that composed, going back to this chemical analogy about valency, he actually was able to express the intuitions behind these equations and the inequations. So I'm going to give you Peirce's description of these statements that very much, I mean, it's kind of hard to say. Peirce didn't know category theory at the time. He didn't know and understand all of the meaning that went into Cartesian bicategories. But when you read these statements I think it's fair to say that Peirce understands the intuitions behind them. So here's an example. These are the Frobenius equations. So Peirce says that quatridentity, which is this term for a node with 4 points coming out of it, is obviously composed of two teridentities. That is, this is the same as this, is the same as this or this. Here's another example. He says the line of identity, so just the regular wire, must be understood quite differently. We must hereafter understand it to be potentially the graph of teridentity, by which means there will virtually be at least one loose end in every graph. So these are those units. Now he also gives the special equation, but I didn't write it. So he's aware that if you compose two teridentities, it's the same as the wire. And he gives natural language descriptions of these inequations for inference rules. So this is Peirce giving the fundamental rules of graphical transformations in 1903. So this is the rule of erasure that I described earlier. Any partial or total graph can be erased. This is now adding lines of identity. We erase them. And he says specifically this rule is to be understood in the beta version as permitting the cutting of any line of identity. So now we can take a line and we can break it in half. And this center one isn't quite, we have to do a Frobenius to kind of rearrange some wires, but it's the same. It involves the cutting of a line of identity. And any partial or total graph may be iterated within the same area. I'll give an example of this, but he's clear that the new replica must have the same junctures, so the same wires that come as the input of the relation and the output of the relation. So I'll give an example of this. Here we take a relation. We have this identity wire coming out of it. We kind of open it up and expand it into two teridentities. We use that process now where we duplicate the relation, sending it to both sections of the wire. We can now cut the wire. We can erase the relation, and we can return back to the relation that we started with. And this is a graphical depiction of the left and the right direction for this equation, which is important. And this is actually, I think, basically exactly Peirce's version of the iteration and de-iteration rule, where we can copy the relation so long as we have junctures corresponding to the wires that capture the domain and codomain of the relation. Now, Peirce even had something kind of like what I just showed you in mind. He has one passage where he says, and again, this is 1907, so he had no TVs or anything like that. At least, yeah. He says, if upon one lantern slide, there be shown the premises of a theorem as expressed in these graphs, and then upon other slides, the successive results of the different transformations of these graphs. And if these slides in their proper order be successfully exhibited, we should have in them a veritable moving picture of the mind in reasoning. So it's kind of a neat way of depicting these graphical transformations. And now we move, so that's to show that Peirce's rules for the beta variant of the graphs on the sheet itself match up with those for Cartesian bicategories. And then when I first started this project in Estonia with Pavel, we were interested in whether you can extend that by adding negation. And so we returned to Peirce's work, to those rules that I gave in alpha, and tried to show how those inference rules can be used to add negation to Cartesian bicategories. And so the first step in this is we follow that principle of contraposition, where now we add this cut and we change the direction of the implications. And when we do that, we get the opposite of Peirce's rules here. So we had erasure, now we get insertion, which is add in an odd number of cuts. So within a cut, any graph can be inserted. And Peirce adds that this rule is to be understood as permitting the junction now of any two lines of identity within an odd number of cuts. And the iteration de-iteration rule now applies through a cut context. So we add these new replica which in that example that I just showed, where you have, we duplicate the relation in the two wires, but now we can move one inside a cut. And likewise, if we had a relation on the outside, we can move it back out. So any graph, if it could be so iterated, may be de-iterated by erasing a replica. And so with those three rules, and we have these two more at the bottom, but those just assert that lines of identity kind of pass through the cut, that the topology of the lines are not affected by the cut. So with those three rules, we're able to extend the string diagrammatic calculus for Cartesian bicategories to add negation, and so get a presentation of first-order logic, a modern presentation of first-order logic. Now that was kind of one of the first things that Pavel and I did. So this is 3, almost 4 years ago now. We have a newer paper that shows how Peirce had. It's again motivated by Peirce, and it shows that he, by emphasizing several other rules, we can give an account of first-order logic that doesn't take negation as a unary operation. So negation is no longer primitive. What's important is the dual of relational composition. And then you have this thing called linear distributivity, and Peirce actually expressed these things in a very old version, even before of a presentation of the algebra of relations, even before he had the graphs. So that served as further inspiration. But for now, I guess you can see this in this paper with Pavel and I, this connection to Cartesian bicategories. But for now, the result here, that I think the takeaway is that Peirce developed similar inference rules and intuitions as those found in Cartesian bicategories. All of this came from his concern for developing a better logical notation and his concern for compositionality, having this pteridentity and seeing relations as like chemical compounds and molecules where you can combine them. And further, his insight serves as inspiration for adding negation in contemporary work for Cartesian bicategories, and then this further project that I just mentioned about what are called first-order bicategories. And I take this to kind of substantially show or just be a nice example of how a concern for notation, even if it was 100 years ago or if it was seemingly distinct from present work, could still lead to some kind of remarkable results and some remarkable ways of thinking about math and logic. I'll end with a final quote from Peirce. He says in a letter to William James in 1909, he says, "My existential graphs, by which all deduction is reduced to insertions and erasures, and in which there are no connecting signs except the writing of terms on the same area enclosed in an oval, and also heavy lines to express the identity of individual objects, this ought to be the logic of the future." And so that was over 100 years ago, but he's not at least too far off, it seems. Thanks.
Thank you. Yeah, hold on. Let's see where the the reactions. There we go. Thank you very much, Nathan. This was fantastic, and you even answered before I got to ask a question at the very end, which seemed, as you said, that part of this kind of makes you think that negation isn't necessary, that you can get it through an insistence on a duality, basically.
Which
is a much more modern way of thinking about it, but it harkens back to 150 years ago. I wonder, though, and this is one of the things I'd love to think more about. I wonder, and I'll say this, and then I'll open it up to anything anyone else might want to say. But what I'm left wondering about is the power of this of his insistence that you brought up on the I guess trivalent connection, or whatever you called it, where basically that in some sense that is really the essence of that all relations can be served that way, right? There's always a dangling thing, which to me also connect with some notions in formal in sort of formal linguistics, where there's some theories for how you can decompose all syntactic trees down to basically that type of object, essentially, and there's an asymmetry to the two branches as well, typically in that case. But I'm left thinking that I want to explore that more and to see for myself what difference that would make if I was to rewrite standard logical inferences in that way. I wonder if you or anyone else has other thoughts or anything to say about that.
One thing that came out of the most recent paper, so this first order bicategories, where you do negation isn't taken as primitive anymore, but you start with, is that this move to triadic like this pterodentity relation, right?
Identity.
It allows you to generalize from binary relations to n-ary relations. And there's kind of, I think, an interesting in the history of logic, there was kind of an interesting move where binary relations seem to be sufficient. And I think most logicians actually still kind of think in binary relations or think that it is sufficient. But this is Peirce's insistence on pterodentity was because he insisted on going beyond mere binary relations to express higher relations. And some of the positive results that we have in this first order logic paper or first order bicategories is that some of the limitations of Tarski's relation algebra come from it focusing merely on dyadic or binary relations, and we can overcome them by generalizing them to higher relations by using just this pterodentity. And that I think is very neat. There's probably going to be a longer story about why that's the case and what exact advantages it gives us. But there are definite advantages there. And just as an aside, I think one thing when I started this work and I was starting to look at string diagrams, one thing that I very much appreciated about them was that they seem to insist on pterodentity kind of from the beginning. Like you have this branch, and it's also been nice to see that that's been kind of pleasantly affirmed. So I think the use of string diagrams is really coming back in some ways to some of these ideas, but it also affirms Peirce's insistence on pterodentity.
Are there any other thoughts, questions, ideas?
Yeah, sure. I think something finally clicked in a certain way when you like sometimes you just need to hear the right words.
Nice, yeah.
In the presentation. Because I was kind of wondering, like when you were presenting the bicartesian category, and you were saying that Peirce did not need to include these equations, right, Frobenius, and would you say, but it kind of feels like when Peirce defines the notion of a line of identity, there's already kind of the principle of that what it does is equating things, and thereby he's observing maybe Frobenius law as a consequence of that interpretation of the line, which is why he first conceptualizes what that line is, and then the inference rule are in the next step. Whereas in the category, they're kind of defined at the same time, right? Like you define what a line of identity is at the same time as you do the inference, or at least.
Yeah.
Is that kind of what's going on, or is it?
I think so. Yeah. He has complete topological freedom in how he uses the wires and how he both when he writes them and when he describes them. And I think you're right. He kind of after the fact notices that some of these other connections hold by how you can compose pterodentity and stuff like that.
Yeah, it pops up in multiple ways, right? Because you have the principle or the idea of conjunction, which also kind of infers that you can move things around already.
Yeah.
Right? So
it's
like it happens on multiple levels.
Yeah.
All right.
Any other thoughts? Where do you see this going, Nathan? What are your thoughts for next steps here?
Well, this most recent work on first order bicategories is interesting because it doesn't it's first order logic, but it also has two components that are kind of different from each other. So one of them is actually corresponds more to the multiplicative fragment of linear logic. So linear distributivity and star autonomous categories kind of work on that side. And it's neat, I think, to explore that aspect of these rules in the graphs. So Priya, for example, does work on linear distributive categories. You have these linear negation laws, and you have linear distributivity and linear negation, and exploring what those look like graphically, I think is really interesting. The other thing that came out of the first order bicategories paper, so this is work with Filippo and Alessandro De Giorgio and Pavel, I guess Filippo Bonchi and Pavel Sobczynski too, was that we have a completeness result for this. So you can write out an inequation as a graph and reason about it, and I think that's really interesting, because now we can somehow kind of reason about, like, we can give axioms in graphical form. And one of the other things that I really like about this approach is that, which I didn't get to show like cool derivations using this graphical method. This is kind of just the very first step of this. But when you write some of these graphs, a lot of these larger inference rules end up turning into topological deformations, where you either like rotate a graph around, or you manipulate a line of identity in a certain way, you add a double cut or a scroll in specific places. And I'm really interested in how these topological moves can help us better understand logical operations, mathematical operations, logical operations like that. So those are kind of three related but three directions that I'll be continuing to work on.
Go ahead, Niels.
Yeah, so now I'm kind of understanding. So the little graphs that you showed at the beginning with associativity and symmetry, just having those on the sheet of assertion will allow you to use the inference rules to then commute any other sum that you might find on the. All right.
Yeah. So one example, so I guess I kind of let's see if I can still do this. I actually gave some examples of this, but I didn't get to making them actual pretty. So these are pretty-ish pictures maybe, but so for example, if you wanted to reason about reflexive relations, you could write this graph on the left and then use all the same inference rules, and the conclusions that you would draw would be those that hold for reflexive relations. So it's just kind of a neat way of, normally we would have to write these out as in equations. We could write them kind of relation algebraically by doing composition, but it's neat that these now are graphs and we can actually manipulate them topologically as graphs.
In the interest
and that's actually how Peirce used them. So in some of his graphs, right. And then sorry, Ted, I'll go back, but
no.
The Lau lectures when he gives. Sorry.
I'm glad you're saying that. This is building on what I had in mind. Yeah, go ahead.
Yeah. So in some of the more complicated graphs that he gives in the public lectures on these, he gives algebraic kind of systems using graphs themselves. So he writes things like this on the page, and then he goes on to elaborate what they mean. And so he intended to use the graphs that way. And that's one thing that I think is also nice about this first order bicategories picture, is that we basically confirmed with this completeness result that you can reason that way. And that Peirce was right to use the graphs, the rules that he did in that way. And that's a direction that I'm very interested in, is now I'm converting like all of these kind of known relation algebraic expressions into graphs and just playing around with them and seeing what they look like and stuff like that.
So what I was saying is, in the interest of connecting this even more explicitly with the compassionate math idea, right? And from my perspective, basically that has to do with the sense making in math and allowing multiple sense making paths, let's say. Might it be possible? This is very speculative, but I wonder what you guys think. For this type of reasoning to become primitive, or to be primitive for someone in some setting. So rather than what our intuition is, and I think maybe what Peirce's originally was as well, to go from this and show how this actually instantiates what we would put in traditional language, let's say. Instead, to for example, in a school context, let's say, or in a context where you're trying to teach first order logic, to communicate an inference, might it be possible for this to be the primitive sense-making modality, rather than have to revert back to say, oh, okay, this works because of the fact that it says what I would say with language. Imagine you didn't have language, or we're trying to communicate something, to an alien civilization that doesn't have this, the same formal language structure. Do you see where I'm going with this? You proved that formally it's equivalent, but I'm wondering if this could be more intuitive. Could we when we manipulate this, could we not simply manipulate it syntactically, in other words, formally, but actually be intending meaning with this, actually this carrying a semantic meaning, by itself, without it being translated to language? I don't know if I'm making sense, but
I think to the early point that we can, I mean, I might be the only one who right now reasons almost solely in this. I'm a big fan of Peirce in this way, right? So I do a lot of my reasoning this way, but it's not unlike how people in category theory use string diagrams all the time, convert everything into string diagrams, right? And the suggestion, the kind of hope, or the kind of bold claim about that is that we'll be able to teach string diagrammatic reasoning in various fields, right, moving forward, and that it will play a role. Like we'll have a graphical linear algebra course in college or university, or even further down in high school. And I think very much this is, I kind of believe this should be the way that we teach logic, at least as an alternate option to logic. And I think it has a number of advantages. I kind of hope that it trickles down and has other adherents and stuff. But it's also brand new. Like there's this notation was largely kind of understudied. It's largely unknown, and there's really not that many people who work on it. But yeah, I'll be a proponent of it for a while.
It's not exactly, I don't think that I'm communicating. I agree with everything that you said, but I'm not sure that you're touching on the thing that sort of animated my question. Probably because I didn't express it clearly enough. And it's bear with me for a minute. I think many people are left with the impression that when you manipulate, for example, category theorists, when they manipulate string diagrams, or when a logician manipulates, formal expressions in Boolean logic or whatever, they're left with the thinking that this is entirely formal. Sort of like someone who does algebra. You just follow your nose, and whatever comes out, well, it must be true because I followed the rules adequately, right? So you're not carrying along meaning, you're carrying along syntax, and then you hope, because you have belief in the rules, that then there will be meaning at the end. But you always sort of, so I'm wondering if there is an alternate, if string diagrams of this kind, let's say, just to take this as a concrete instance, can also be an alternate meaning carrying mechanism, like, for example, inside and outside, or other modalities of meaning creation and manipulation, right? So that it's not strictly formal, right? But
it's not merely formal. Yeah.
Right. And I think maybe what you're saying is that someone who has done it enough, like you, actually it feels that way. So what I'm thinking is, could we have, for example, a game environment, some sort of interactive environment to familiarize, say, young students or novices to this? So before they start thinking, oh, this is instantiating something that I already know in a different context. So you're always reverting to that. And you're sort of building meaning, primitive meaning in this context. I think this might be powerful and generative.
Yeah, so that's, when I use the graphs, that's often how I use them. Peirce, I think, is interesting because he actually very much intends for it to be the way you describe. So one thing, the way that he starts and motivates them, right? He's just taking natural language expressions, things that, when we write a sentence, we already kind of conceive of what the meaning is, and then we write it on the page. And now he actually describes it. I think it's neat that he describes it this way. He says, now we're kind of performing an experiment, just like a scientist would in the lab, but it's diagrammatic in front of us. And so we can manipulate it and potentially learn new things ourselves about that concept based on the graphical transformations we've made with it. And this, I think, is also, Peirce spends a lot of time distinguishing what he says is the work of the logician from the work of the mathematician. And it actually falls kind of on a similar distinction here, which is that the logician for Peirce, at least, is really focused on clarifying our own conceptions. So it always starts with something that we are kind of familiar with. Peirce thinks the mathematician is rather interested in this like merely formal project. And I think it's also kind of a shame in some ways that logic tends to be taught as this formal way, right? Where we just say, let's assume, a list of variables and a list of, like these things are not, they're so far removed from how we actually think in the familiarity we might have with the concepts as we employ them and as we might be concerned with them, right? And so Peirce's kind of dream, and he connects logic up with scientific practice in this way too, but he very much sees the aim of logic to be clarifying our actual thoughts and using the diagrams as a way of better representing those thoughts and as a means of performing manipulations and experiments to learn new things about our thoughts. And so so it's neat that I just draw that connection, that it's neat that Peirce very much seems to think in that way about the graphs.
Thank you. Yeah. Is anyone
there's
familiar?
also
Yeah,
oh,
go ahead.
sorry. I
No,
was
no.
going to say there's also this issue that logic is not even taught at many places. So uh, I think the few of us who have seen logic in courses, I think we are more privileged among even mathematicians. When the mathematicians live out their careers and get scared of logic. That's my experience in talking with people. And Yeah, I feel like we should have more logic courses at from school years. That's the only way to really get rid of this issue that people are somehow scared of logic.
Which is surprising in a way in this generation where everything has become so, in a way, so computational, right? Like mathematics even, and the applications of mathematics are seen as moderated through computational means, through literally through instances of logic in the computer, yet somehow that hasn't really, like, we haven't drawn the connections in some ways explicitly, right? Like in our education system or in the ways we still treat them as separate, that we don't focus on the logical bases and how the logic is instantiated.
Yeah.
I was wondering if anyone is familiar with or is aware of diagrammatic methods of this kind being used in the context of AI.
Not yet, not that I'm aware of. So
Okay. Yeah, and I'm thinking both in terms of like, implementation. I mean, both sort of to implement other things in logic and so on, or to analyze, what's going on. I mean, obviously, the string diagrams can be implemented, in various contexts, like on the computer, and therefore they could be raw material for a generative AI system, just like language is, right? So I don't know if anyone has sort of taken that step to look at, at collections of statements that can be legal or illegal in this way, and sort of train an AI to generate new ones. It seems easier in a way than formal than language, than natural language, right? Because it's a little more fewer symbols. Well, thank you very much, Nathan, again, for introducing us to very fascinating world that goes back. I mean, it's really amazing. It's the kind of thing we've talked about repeatedly, right? How how modern ideas really go back a while, right?
Yeah.
But it's so underappreciated. So thank you for bringing this to our attention and for starting us off on, I think, a wonderful adventure. I'm certainly going to be thinking much about this.
Yeah, I want to add to that. I've come across this work of Peirce several times looking at the history of mathematics, especially sort of he was one of the significant early mathematicians in the US. But sort of working quite, and I'm very happy to have actually seen the details laid out and seen how it relates to more modern theories. So I really appreciate that.
Thanks.
Okay, bye-bye.